意志や意識は幻想なら、生物の行動は自然本能の反射なら、知性や文明など存在しない。なぜ、猿はいつまでも人間になれないのか。YouTube に茂木健一郎氏が上げている映像で、自由意志は幻想で存在しないことを受け入れると、かえって自由になれる、と題する映像がある。1年半前くらいに投稿されたようで、まず、自由意志は、量子力学によって発現するという人がいるが、量子力学の基本原理は確率的なランダム性だから、そこから明確な意志とか企画とかを生じさせることはできないと茂木氏は言う。しかし、自由意志が量子力学によって成立する場合、量子力学は微細粒子の非局所的な集団運動だから、一見すると統計的なランダム性のように見えるが、他の科学分野では、半導体利用など微細域でのテクノロジーのほとんどは、量子力学を基礎として成り立っており、PC やスマートフォンその他レーザー発信あるいは超電導などが、量子力学を基礎として展開している。さらに、リベットの実験を例に挙げて、神経電位の発信が見られてもそれを拒否できるから、倫理的には問題ないと茂木氏は言われるが、リベットの実験では、この拒否について、新たな拒否信号としての神経電位からの拒否電位は確認されず、実に曖昧に決着している。この点について、茂木氏や他の唯物論者は、脳の無意識領野が拒否を決定して、それが行動になるというが、神経電位発信とその拒否があれば、それは自由意志になり、犯罪実行は、ほとんどの場合、無意識で実行されることはない。量子力学から見れば、神経繊維は明らかにマクロ構造であり、人間のある行動期との時に関係する神経から電位発信があったとしても、今までの人間経験である想像イメージによる変幻自在な展開や、思考での想像イメージの構成や明晰な意識と夢との区別など、古代からの生物全般の進化過程において、20世紀初頭に発見された量子力学が何らかの役割を果たしていることは否めない。
Zachary Cochran, thanks so much for coming on to Evolution Soup all the way from your office in New York. You are an assistant professor of anthropology at Vassar College, studying human evolution, growth, and development. As a biological anthropologist, you are well aware of all the reasons why human beings are not just related to apes, but actually are apes, which is what we're going to be discussing in depth today. So, how are you doing, Zach? The past few weeks have been pretty hectic for you, but I know you like to get out and about and go for a run now and again. So have you had the chance to do that, or has your workload at Vassar kept you chained to your desk?
So the workload is your typical end of the semester persistent pandemic workload. It's fine, but the main thing keeping me from enjoying a nice run is the weather, because you've kind of shifted back into more winter-like conditions. It's not quite snowy, but it's pretty cold and pretty gray.
Well, before we get deep into the reasons why humans are apes, let's just hear a little bit about your background. Now, you started out your academic career in Michigan and also spent a good few years as an assistant professor in Kazakhstan before moving to Vassar. But you also worked on the Homo naledi fossil, isn't that right?
I grew up in Kansas City, Missouri, originally, and then I was from kind of that time, I was always interested in the past, starting off in the more recent past with things like, ancient Greece and ancient Rome and all of that. And then when I got to college at Loyola Chicago, I discovered human evolution, and it just kind of blew my mind to think of a time and really kind of an existence when humans weren't really the same as we think of ourselves today. And so that's kind of what led me to then go to graduate school at the University of Michigan, where I kind of really delved into fossils and the study of both evolution but also growth and development. And then I finished my PhD and I went to Kazakhstan for a couple of years, and then Lieberger and colleagues had announced that they had some new fossils that they were trying to get a bunch of people, experts in various fields, to come and do preliminary descriptions and analyses of. And so I came out as part of this group that was focused on growth and development, which is very tricky to study in fossils because, or rather in extinct species, because you generally need large sample sizes and representation of lots of different ages throughout the growth period. And you don't usually get that with fossils. And so that's what my dissertation work had been on at Michigan, and that I worked on a little bit more while I was in Kazakhstan. And so, so over the past couple of years, I've been working on various aspects of growth and development in this fossil species Homo naledi, which existed about 300,000 years ago or so, probably in South Africa. And we actually just a week or two ago had a paper come out where we had described and analyzed this very tiny little hip bone of a juvenile Homo naledi. And so I'm very excited to see that one come out finally, because it took a lot of work, and I'm really thankful to all my collaborators and colleagues for their persistence in this as well. So there's a lot of Homo naledi material, but it's all very tantalizing, and it's a little bit too much at times, and so there's a lot of fun stuff to do with it in the works.
Okay, let's get a little history on human evolution and our links to apes. Zach, is the human-ape connection relatively new knowledge, or does it go back further than perhaps we realize?
Yeah, it's actually been pretty well appreciated by various scholars over the past millennium or so. Most recently, there's been a lot of, with the rise of genetics and genomics research, there's been a lot of work that shows pretty clearly that humans and chimpanzees are genetically most similar to one another than either of them is to any other species that is alive today. And there was some preliminary evidence suggesting that as well, kind of before we had true genetic data back in the 1960s and 1970s, showing again that chimpanzees and humans are remarkably similar to one another. But this was also appreciated pretty well by a lot of the naturalists that really kind of helped develop the theory of evolution early on, such as Charles Darwin and Huxley and people, recognizing really the concept of homology, this principle that, when we look at like our 5 fingers on our hands and the 5 fingers on, an ape's or a monkey's hands, that's not just a coincidence. We inherited that from a common ancestor, and so that similarity reflects a shared evolutionary history. But even earlier than that, there's a article that came out a few years ago highlighting a lot of the work in the writings of medieval Muslim scholars like Ibn Miskawayh and al-Biruni from around the 10th and 11th centuries, where they recognize a similarity between humans and apes and monkeys, and posited that perhaps humans evolved from one of these other primates or something like one of these other primates. So just the overall similarity that we can see between humans and especially the apes really has been appreciated for a while, that we have this kind of special connection that now we appreciate reflects our shared ancestry.
Well, let's just kick things off by stating what we now know about human evolution and the human lineage.
Okay, so we know basically from a combination of genetics and paleontology and comparative anatomy, among other scientific fields, kind of what changed and when. And so from genetic evidence, we know that humans and chimpanzees share a common ancestor with one another on the order of around 5 to 9 or so million years ago. And then from there, using comparative anatomy to see kind of and kind of be not just anatomy, morphology, physiology, seeing how humans differ from our close living relatives, the other apes. We can start to document the differences and say, okay, well, if the apes all share these features, but humans look this way, that means this is something that changed over time, such as our brain size or our small canine teeth or something like that. And then we can go to the fossil record, the paleontological side of things, to see kind of when the major changes happen in a geologically time-constrained way. And so what I think is one of the cool things about the paleontology side of things is that, when you look at humans and compare us to the apes, you would say, okay, well, we stand on two legs and we have these big brains and small faces and we use these tools. That's what basically Darwin and people first jumped to. And so there was a lot of emphasis on the brain early on. But the fossil record shows us that brain size was small for a very long time. And the very first thing that really distinguishes hominins, or the early human ancestors, from the other apes is walking on 2 feet, on 2 legs. And so we have good evidence of bipedal walking on 2 feet, about 4 million years ago. But at the time, canine teeth are still fairly big, the face sticks out a lot, brains are still small. And then we can see, from, again, following the fossil record, shortly after that, we see the emergence of stone tools. And so probably technology is starting to be incorporated into the niche now of early humans. Brain size kind of gets a little bit bigger along with body size in the early members of the genus Homo around 2 million years ago. We see a kind of a reduction in the adaptations for climbing, suspensory adaptations, we call them, things like having really long fingers with curved finger bones that help have a really strong grip on branches. And brain size reaches its kind of overall modern human-like proportion probably a couple 100,000 years ago, but some cool work by people, actually lots of different researchers, but a lot of work especially by the group from the Max Planck Institute shows that it's not just brain size that changes, but also like the shape of the brain, which we can get from the internal surface of the skull. And so we don't have a more modern-like brain shape probably until, I don't know, around 100,000 years ago or so. And so we can use these various lines of evidence to kind of piece together how we went from something that was probably, anatomically, behaviorally very similar to the living apes to these just kind of really weird, bizarre animals that we are today.
Zach, there are a lot of misconceptions and misunderstandings floating around out there concerning evolution, and especially, it seems, human evolution. So let's just address these one at a time, starting with the most common one that we hear. If humans evolved from apes, why are there still apes?
One thing to keep in mind is that the apes themselves, the non-human apes that are still alive today, are, it turns out, a very small subsample of the great diversity of apes that existed millions of years ago. And we know this from the fossil record that, 20, 15, even about 10 million years ago in Africa, in Europe, even in Eastern Asia, there are actually a number of ape species that evolved to live in all kinds of different niches. And so a lot of the apes that were alive millions and millions and millions of years ago are actually not very, they lived in different habitats and ecosystems than modern apes do. And so, we did not evolve from any of the living apes today, but rather humans and all the living apes today share common ancestors in some of these apes that were alive millions and millions of years ago. And so I guess the big misconception there is, we tend to think of, well, these are the apes that we know of. These must be the apes that always existed, and so we have to have come from one of these. But really what the fossil and even genetic evidence shows is that we didn't evolve from any of these animals, but rather we share a common ancestor with them in the deep past millions and millions of years ago.
So the next question, Zach, is, are gorillas, chimps, and orangutans just a step away from becoming human?
The living apes will almost certainly never have the opportunity to evolve into humans. And that is because evolution isn't really goal-oriented. It's not moving towards some specific target. It's not as though animals evolve from one condition and then necessarily have to pass through different phases to ultimately reach some kind of common goal that we could think of as being human or something like that. But rather, each species will be subject to evolutionary pressures within a specific environment. And so for these various kinds of reasons relating to just the historical background of what these apes are and what their genetic variation is like today, and the uncertainty around, what environments they might find themselves in the future. It would be statistically extremely unlikely, to the point of essentially being impossible for them for anything really, to evolve into humans.
I think a lot of people think that it's like human beings are like what every primate is almost striving to become, which is not correct.
Yeah. I think we all like to think of ourselves as being pretty great, and I'm sure a lot of us are very great. But in terms of animals and organismal evolution, there aren't targets or goals. It's really just, surviving, adapting to environments, or going extinct.
Yes, because I think there's the Paranthropus line about 2 million years ago, and they kind of reached an evolutionary dead end. But if they hadn't, they might have evolved into something similar to us, but not necessarily they could have stayed very similar. Isn't that right?
Yeah, actually, I like to think about if those robust Australopiths, Paranthropus, or however you like to call them, if they had not gone extinct, what would life be like today? These little kind of almost humans or kind of humans
or maybe
running around. Or, knowing how modern humans interact with animals, it probably would not end very well for other hominins. But in that case, actually, that's an interesting point that I hadn't thought about. If something could potentially become kind of more like humans, it would be any of these extinct hominins that are already kind of more like us.
Yeah, but it depends on the pressure. I mean, what caused us to have a bigger brain and to lose our hair and all that, that's not necessarily going to happen to any other hominid, is it?
Right, probably not.
Okay, the next question is, why aren't humans evolving anymore?
So that's an interesting question, and it turns out that humans actually are still evolving. One kind of misunderstanding that I think relates to the other question about, why apes aren't becoming human is that, if humans are kind of the end-all be-all of evolution, then we couldn't possibly evolve anymore, right? We've kind of hit the end of the road. But it turns out that as long as there is genetic variation, and as long as there are, subsequent generations in the future, any animal, humans included, could continue to evolve. And when we look at humans today, there's actually ample genetic material for natural selection to work with because there's so many humans. And even though we're all fairly similar to one another, these subtle genetic variations create, the raw material for natural selection to potentially increase or decrease the frequency of in the future.
So what are the tried and tested peer-reviewed evidences that we have today which show that human beings are members of the great ape family?
Yeah, so there's a lot of evidence that we can look to. On the one hand, the genetic evidence basically looks across an entire genome, all of the genetic material that an animal has. So you can compare the genomes of humans, lots of humans, and lots of apes, and lots of all kinds of different animals. And the general principle is that the more similar animals are to one another, the more closely related they are, the more recently they shared a common ancestor with one another. And so those kinds of studies have shown pretty clearly that humans and chimpanzees are most similar to one another, more so than to any other organism. And so that shows that not only are humans, closely related to apes, it's not as though you have apes on the one hand and humans on the other hand, but you have humans and chimpanzees on the one hand, and then, we're more closely related to one another than either of us is to gorillas, orangutans, or gibbons. So on the one hand, the genetic ancestry shows us that we're very much nestled within this group of apes. The anatomical evidence, going back to our concept of homology, these shared features that we have with other animals, a very fundamental one. And if you look across the skeleton, we look like good primates. good anthropoid primates, to use a fancy word. So humans, apes, monkeys, we have eye sockets that are fully enclosed in bone, which is something that is very rare outside of our group. So that's something that tells us, okay, well, yeah, we're primates. But one thing that makes apes unique compared to monkeys is that monkeys will have a bunch of vertebrae coming off of their sacrum, their kind of back hip bone. They have a bony tail, and apes don't. And so humans are actually very similar to the apes in having a coccyx as opposed to a tail. And so that's something that again, unites us with the apes. We have a lot of features in our trunk, anatomical features in terms of our muscles and our kind of our bones, how the muscles are configured on our skeletons that reflect this common heritage from some kind of an ape that would be suspensory or basically, hanging from branches. Our teeth are very similar. Of course, we have reduced canine teeth and smaller incisors, and there's some subtle anatomical differences. But human teeth as a whole, especially our molars, are going to be more similar to the living apes than to monkeys or any other animal for that matter. The fossil record shows us as well is that as you would expect if we evolved from an ancestor with the apes, the earliest humans, or the earliest kind of members of the human lineage that we can see in the fossil record, look very similar to the bones that we see from the great apes, especially gorillas and chimpanzees. That again kind of highlights this common evolutionary origin.
That's right. I know when I look at like Lucy and Africanus and hominids like that, their pelvis is very similar to ours. And they're not like for instance a chimp's flared out kind of pelvis.
Yeah, so the pelvis is fun because this is one of it's 3, 6, like 10. It's a whole bunch of bones that we kind of think of as a whole unit, right? And these have been very dramatically reconfigured over the course of human evolution because it's critical for how we walk on 2 legs, how we are able to support our bodies with this really weird way of getting around the earth. And the earliest hominins, for which we have good fossil evidence, do show a lot of these similarities with, or these bipedal adaptations that we have today, such as, basically being shorter and, like you said, not quite as flat flaring. But some of these early hips, like Lucy, like Australopithecus, and actually even like Homo naledi, which is one thing that we've shown fairly recently, they do have the general plan of a bipedal pelvis, but it is a little bit flatter. So in a way, it actually forms a nice kind of intermediate morphology in a way between the ape pelvis, where the hip, the ilium bone is really flat and facing towards the back, and humans where it's more round and short and kind of facing more towards the side. So with Australopithecus, it's a little bit intermediate there, which is pretty cool.
Zach, we've all seen that famous illustration where the lowly gibbon gradually becomes the upright walking modern man of today. This so-called march of progress has gone through quite a few iterations over the decades, but it's not exactly accurate, is it?
Yeah, that's correct. So part of that gets back to one thing that we were talking about earlier, where, the evolution of life, or the history of life, isn't just, animals trying to get from point A to humanity or something like that, but rather organisms, will move into new environments, or climate will change, habitats will change for whatever reason, and organisms have to then adapt over time. Populations will change over time, or they will go extinct. And so what this means is that you don't so much have animals progressing from early to late or, ancestral to advanced, but rather there's basically a proliferation of species, of new species on Earth. And so, we'll talk about a tree of life as opposed to, a linear trajectory, but, there's like a branching of animals as they share one common ancestor in the past. Over time, they will diverge and become different species, so you have this kind of branching process. And more recently, there's a lot of analogies in the realm of like a braided stream of evolution, where now we know, especially from studying living animals today, but also genetic evidence from fossils, from Neanderthals, Denisovans, things like that, these early hominin populations might have diverged from one another early on, but they also probably came back into contact with one another and mated, exchanged genes. And so you have this really fascinating picture of human evolution where it's not as simple as a straight line from start to end.
No, it's quite messy, isn't it?
It's not as fractal-like, I guess, as like just an explosion of species, but rather there's this explosion, but then this kind of coalescence and redivergence and all that stuff. So I don't know if redivergence is a word. I think I might have made that up, but it's messy. It's messy, but that's what makes it interesting, I think.
Well, human evolution has been a very popular topic on this channel, and no doubt we'll have you back on the show in the future to talk more about your work, perhaps some more detail on your work on Homo naledi. So what projects have you got lined up for the future? Anything you can tell us about?
Yeah, I've got a number of projects that I'm, in various stages of that might seem kind of disparate, but the common theme is evolution and development. And so I've got a paper under review right now with some colleagues describing a brain endocast of an Australopithecus, probably juvenile or infant, from a site called Makapansgat in South Africa, dating to almost 3 million years ago, probably. So that's a lot of fun. I've been getting more into kind of brain stuff. And so, there's the fossil side of things that I'm still very much interested in and enjoying. But I'm also starting a new project looking at gibbons, living gibbons, as a model for hominin diversity. And so this idea came from a collaborator named Dr. Julia Zucchello, where she just kind of highlights all these reasons why gibbons are an underappreciated and kind of a forgotten about potential model for early hominins, because there are like 20 species of gibbons that are alive today.
And they like walking upright, don't they?
Yeah. My colleague Jerry De Silva and his collaborators had a paper come out just a few days ago looking at, I don't know if you saw that.
Jerry's been on the show,
Yeah. I saw that.
He was good.
Yeah. We went to graduate school together. That's where I first met him, and so we've collaborated on a few things. But yeah, here's a cool paper that just came out looking at rates of or frequency of bipedal walking among apes in zoos, where, like you said, they show that gibbons, when they are on the ground, walk on two legs all the time. Like they're pretty good at it. So that would again suggest maybe a Hylobates or gibbon model for early hominins. But so right now what I'm looking at is basically their skulls, looking at the impressions of their brains that you can get out of the skulls. So yeah, hominins and gibbons. Wow. Fast times.
And do you think, you said that the Makapansgat Australopithecus is about 3 million years ago? I'm immediately thinking Lucy and Afarensis. Could it be an Afarensis?
So the site of Makapansgat it's actually got a really...
意志や意識は幻想なら、生物の行動は自然本能の反射なら、知性や文明など存在しない。なぜ、猿はいつまでも人間になれないのか。映像に登場する進化人類学のザッカリー・コフラン博士。多くの人は、すべての霊長類が人間になりたがっていて、すべての生物の最終目標のように考えていますが、それは正しくありません。動物と生物に関しては、 それぞれのターゲットまたは目標があります。それは適応して生き残ることを知っているだけです。現在の進化人類学はいずれ猿は進化して人間のように言葉をしゃべり文字を書き PC を操れることを完全に否定します。今から約700万年前の古い時代に猿とも類人猿とも分類できない類人猿の祖先がいて、それが猿の祖先と人の祖先に分かれたと言われている。そして現在それぞれの進化系が現状に適応して生存している。猿に分かれた系と人に分かれた系の間に、知性に大きな乖離があることは認めなければなりませんが、その乖離が何の原因で起きたかは、進化人類学では自然にとしか言いようがありません。私たちが人間またはそのようなものであると考えることができるという目標ではなく、むしろ各種は特定の環境下で進化の圧力を受けることになります。彼らの遺伝的変異が今日どのようなものであり、あなたの周りの不確実性は彼らが将来どのような環境にいる可能性があるかを知っています。彼らが実際に人間に進化することは本質的に不可能であるという点まで統計的に非常にありそうにないと思います。ここからは2つの系に分岐した後に人の祖先に起きた可能性のある知性の急激な発展について、それが量子力学と何らかの関係があるのではないかという投稿者の推論です。ここからは2つの系に分岐した後に人の祖先の方に起きた可能性のある知性の急激な発展について、それが量子力学と何らかの関係があるのではないかという投稿者の推論です。現在、人類と他の生物との間には、かなりの知性的社会の乖離があり、それは、生活圏が隔離されているとか交流が途絶されているという中で起きたことではない。他の生物は、意思伝達手段として言葉をしゃべる生態が劣っていたとか、鳥の一種は、人間の言葉を真似る、文字を創発するのに、記憶と関係性の能力が劣っていたというわけでもない。明らかに何か急激な知性的本質の変化によって人類の知性は進化したと思われる。意志や意識は幻想なら、生物の行動は自然本能の反射なら知性や文明など存在しない。なぜ猿はいつまでも人間になれないのか。冒頭のページに挙げたのは、今のアフリカ大陸の野生生物保護区での生態系の現状であり、そこでは食物連鎖として本能によって草食動物を餌にする肉食動物の姿です。それは、その上空には大型ジェット旅客機が飛び交い、地上では観光客を乗せた車が動物の生態を見せています。この光景は動物の生態としては何百万年間変わらず続けられています。動物の形態は環境変化とその適応で多少の変化はあったと思いますが、その本質は何ら変わらずに、生物各々の行動は自然本能の赴くままに動いています。量子力学に比べれば明らかにマクロな系の神経系が被験者の運動意図によって先に電位発信を検知したとしても、被験者は意図の発生を口頭で伝える。そこには意図の発生で被験者の精神に何らかの心的創発が起きたと見るべきである。以下は投稿者の憶測であり、700万年以前の古い時代に猿とも類人猿とも分類できない類人猿の祖先がいて、それが猿の祖先と人の祖先に分かれたと言われている。その後、人の祖先は急激に知性が発達したが、それは過程として量子力学が何らかの影響を与えた可能性を探求する。 投稿者の推論として、人間の生態系に今の知性を与えたのは量子力学だと思っている。それは、量子力学の非局所性の特徴が発揮されているように思える。特に、量子一個の全方面での同時存在と、粒子性という固有占有領域の境界が明確ではないという事実がある。この大自然の局所域に生命性を発現させ、その個体内に自由度を内在させ知性を発展させた背景機能があるはず。野生社会との対比。非局所性によって文字言語の意味認識や理解が人間各人の思考の根底に波及し、人間相互の意思疎通伝達を助ける。眼球から入力される全面風景以外に、非局所性によって多方面からの仮想視認像がおぼろげながら可能になる。量子の粒子性の境界が明確ではないから、マクロな人間が思考を形成する上で初めに行うのは自己形成である。人間の仮想認識像は自己意識や自由意志に現れ、これにより意思行為や自立行動に責任が生じる。人間各人の思考の干渉を防ぐために、思考を行う人間が注意を向ける思考対象は粒子性を帯びる。人間の外界認識は共通の外界視認だから、この時点では量子は粒子性を帯びない。夢知覚は覚醒時ではなく睡眠時の体験だが、この鮮明像は投稿者には説明できず量子的効果だと思われる。投稿者は、金儲け目的で投稿しているわけではないから、視聴者の増減を気にすることはない。投稿の目的は、投稿者の達成感を得ることが第一であり、投稿自体を仕事にすることはない。なぜなら、投稿内容は、時代を切り開く役割のために、新規かつ斬新なものにならざるを得ず、そんなアイデアを毎日創出できるほど、投稿者の脳は常習的、機械的ではない。